All right, let's start then with this lecture on advanced FEM. But before, we're going to do a recap on isoparametric mapping. So if you remember, the idea was let's not work on a physical element defined by global coordinates, right? But instead, let's try to have a mapping that actually maps to that physical element. So if you remember, this element was called the master element or canonical element. It has different names in literature, but the idea is that in a 1D setting, this coordinate C goes from -1 that maps to that node to +1 that map to that one. And so we are going to use the same shape functions as we use in 1D. So those are the bilinear shape functions, and they are defined in terms of the C coordinate like that. So you have 1 minus C divided by 2, 1 plus C divided by 2. And so now the geometry is basically represented in the same way that we represent the field. And that is the reason why it is called isoparametric, right? The geometry and the field are interpolated with the same functions, the same polynomial functions, okay? Of course, if you have isoparametric, you also have subparametric or superparametric, depending on how you represent the geometry. And normally, when you're going to see soon when we start talking about PFEM, in PFEM, we normally take the field to a higher degree, quartic, quintic, polynomial, for instance, but then we keep our geometry at a lower degree, linear, quadratic at most. And so that is a subparametric formulation, right? So that is one example of a subparametric formulation. And we also talked about, for instance, the use of NURBS. Today, NURBS represent geometry exactly, but you can choose to have your field at a, I don't know, linear, quadratic, polynomial, for instance, and in that case, you have a superparametric formulation, which has actually some issues. Okay, but the idea, why using an isoparametric mapping? Well, we said that it was mostly used for integration, right? So you can take one integral in the usual way we're used to define the integral, but then we change the domain of integration, and the moment we do that, you notice that the domain of integration changes from -1 to +1, and the Jacobian of that transformation pops up, and that is essentially a ratio between the lengths of the physical element to the master element. And so still, we are not doing integration like that. The main idea is now that we are working on a canonical element, we know all the integration rules that are defined on that element. And so the integration is an approximation now, because now we are evaluating the shape functions at a series of integration points or quadrature points or Gauss points, right? And then we have the weight that is associated with them. And that is the way we perform integration. So we do numerical quadrature of the functions that we need to integrate. And then, as an example, we apply this to the local stiffness matrix, right? And the stiffness matrix is actually perhaps the hardest thing that we're going to see in this course, because, well, it involves the derivatives of the shape function with respect to global coordinates, right? But because those shape functions here are defined on the master element, well, we need to apply the change rule, and so we have this change rule that accounts for the fact that we have this mapping involved, right? And then if you notice the stiffness matrix, we end up with the same standard stiffness matrix for the bar element that we all know, which is EA over L, 1 minus 1 minus 1, 1. Okay, and I put here an approximation, right? Where is the approximation? Here. Because, well, normally, depending on the function, you're not going to be able to integrate it exactly unless we're dealing with polynomials. And, well, for this case, we know that 2n minus 1 is equal to p, n being the number of Gauss points, right? So n integration points integrate exactly a polynomial of order 2n minus 1, right? Okay. So that is everything that we're going to discuss regarding the isoparametric mapping. But now we're going to start with heat conduction. Yeah, and I like this lecture very much because heat conduction is that problem where we're dealing with a scalar field, the temperature field, right? Regardless of whether we're in 1, 2, or 3D. So going from 1D to 3D is not that hard, and yet we gain a lot of value that we're going to use later when we are looking at elasticity, right? That is the main thing that I like about the heat conduction problem. So, well, as usually, what we're going to do is we're going to state the strong form of the boundary value problem. We're going to state the weak form of the boundary value problem, and hopefully we get into the discrete equations the same way we have been doing it for the bar. So it's very, very straightforward. Okay, well, strong form. So of course, there are some quantities that have to be given. You need to know the conductivity of your let's say we're going to start with a 1D case, right? You need to know the conductivity. So given K, that's going to be the conductivity. And again, domain is omega, codomain is a real. So this is the thermal conductivity. Then we're going to have a heat source. We're going to have a heat source that goes from omega, again, a real quantity, so it's a scalar field. Heat source, well, find the temperature U, right? And notice that I use U, right? We're going to use U in this course and in the book for everything that is a primal field, right? Doesn't matter. Some people call it T. I call it U, okay? Such that K, the second derivative of U, plus F is equal to 0 for OX that belongs to our domain omega, which is known as the Poisson equation. And if you recall, well, we don't need only the governing differential equation, but we also need the boundary conditions. So boundary conditions, since we have two ends, remember this is a one-dimensional, so we have two ends of our bar, right, where we're going to have this heat conduction problem. Then we're going to have the same type of boundary conditions. So before we have a Dirichlet boundary condition, U is equal to U bar on gamma U. And then K du dx times n, and I'll talk a little bit about this, is equal to Q bar, your prescribed heat flux on gamma T. This is your Newman boundary condition. And of course, you can have something that mixes these two, what we denoted as Robin boundary condition, Ku du dx n is equal to H, and that is your film coefficient, and then U infinity minus U, and U infinity is normally your ambient temperature on gamma H, okay? Of course, embedded in all of these is Fourier's law, right, which is basically minus K du dx is equal to the heat flux, which basically says, well, the negative sign here indicates that the temperature flows obviously from regions of high temperature to regions of low temperature. That's why the heat flux has a negative, is a negative of the gradient of the temperature field. Okay, and this is known as Fourier's law. So that is your problem in strong form. Okay. Now, as we always do, right, we take a problem in strong form and we say, well, again, it's going to be kind of hard to satisfy this exactly. And so we're going to relax this requirement for all x in omega. We relax it, and we're going to do this on average, the same way we did it for the one-dimensional bar, right? And let's see what we get in the process. And so for the weak form, we're going to take our governing differential equation. We're going to multiply that by a test function, right? And we're going to integrate that between 0 and L. And we're going to say that that is going to be equal to 0 from all W functions in some space that, again, we call the energy space. Remember, infinite strain energy. Now it applies the same here. things are not going to heat up to infinity. So it wouldn't make sense to have a gradient, a temperature gradient that is infinite. That doesn't make any sense, right? Things are going to just disappear. So the same thing happens here. The idea, mathematically, is that we should be dealing with functions that we can integrate. Otherwise, this integration makes no sense. Okay? Well, so you have a question over there, right?
Yeah, but I forgot it. So.
Okay.
No reason.
Okay, no problem. Okay, but before we get, let me, because I do have some notes I would like to discuss here. Because, okay, well, you see here, Fourier's law takes this form, right? Heat flux flows in the direction, in the negative direction, the opposite direction of the temperature gradient, right? And so I want to talk a little bit about this, because that sign cannot disappear, and it has been basically absorbed by my normal. And in a sense, the convention that we're going to use here, right? If you remember that we had a convention in the 1D case for elasticity, right? And so we made the conventions in such a way that the sign that we were taking at the ends, right? This normal was supposed to help us to see whether a given force was going to produce negative strain, right, and in compression. So we're going to have the same thing here. And our convention in the heat conduction problem is going to be, well, the moment I apply a Q bar, right, a prescribed heat flux that is positive, that basically means that at that location, heat is entering the bar. Okay? So you can see it, and I will do a quick drawing here that is really not the main part of the lecture, but anyways, say you have a temperature field that looks like this. Right? So this is T1 basically, and this is T2, right? So you have a negative field. Well, if I look at this point here on the left, you're going to have K du dx, and again, I'm looking at this expression here, right? Times n is equal to Q bar, right? That is my Newman boundary condition, and like that, right? Well, if you see the temperature gradient, this guy is negative, and because I am in the left end, this one is -1, so this whole thing is positive, right? So this guy here is greater than 0. Now, if I look at the other end, I have here K du dx n. So this guy here is again negative. This guy here is equal to 1. And so this whole thing is actually less than 0. Okay? And so you see, indeed, heat is flowing in that direction because the gradient has like that. So heat is flowing from left to right, right? Well, we can do the same for the other case. It's going to be something similar. So say we have now a problem that looks like this. So this one here is T1, T2, and then K du dx n is equal to Q bar. Well, for this case, this guy here is greater than 0. This guy here is -1, and so this whole thing is less than 0. And then for the other end, let me move this a little bit. K du dx, and so again, this guy is greater than 0. This is +1, and so my prescribed heat flux is greater than 0, right? So we can say that, for instance, in situations that if I call this 1, this is 2, this is 3, and this is 4, well, in situations 1 and 4, the heat flux into the domain. And in cases 2 and 3, heat flux out of the domain. Okay, so now that, again, just to summarize then this point, the convention, and I'm going to write it down so that you also have it in the notes. The convention is okay, for completeness. Okay, so now we continue with the weak formulation, all right? And so this yeah?
When you mean with domain, I imagine it has a control volume where heat is flowing in,
Yeah.
heat is flowing out.
Yeah, yeah.
And it's located at T2, right?
Is located?
It's located where, so the control volume is T2 and the environment is
No, T2 is your temperature at one end.
Oh, okay. I see.
So basically, this is somehow showing the whole temperature in the entire bar, right? It's just that it has the two ends. So that's why I'm saying I'm expressing the Newman boundary condition at both ends. Okay. Okay. Now that we have discussed this issue with the sign and with the n, and so we are going to finalize the weak formulation. Well, if you remember, we applied. What do we do when we have our function? What did we want to do? The same thing as in the 1D case in elasticity.
You integrate and apply weight. Oh, that's what
We are going to integrate. So after we set this condition to 0, right, where we're saying now we're going to satisfy this condition on average along the whole domain. So what do we do next? We integrate by parts. Why? Because we want to balance the derivatives. Very nice. And that, of course, is nice because it's going to lead to a bilinear form that is symmetric. And symmetry is nice because
it's easier to work with.
it's nice because it's nice. Huh?
We can do half the work.
No. Yeah, well, actually, yes. You can do, if you are using a direct solver, you can do Cholesky factorization, and that is going to use roughly half of the number of operations.
Because second order derivative is too much important statement.
Yeah, it's too much as
Hard to get.
well, it's not hard to get, but it's too hard of a requirement for the functions that we're going to use. So by balancing derivatives, we also are going to be able to use linear functions, right? That was your addition. Yeah, that's pretty much it. But there was something else nice that happened when we did integration by parts. Who remembers?
Cancel each other?
Boundary conditions.
That's all?
Boundary conditions, exactly. The boundary conditions, the Newman boundary conditions, should arise naturally in the formulation by doing integration by parts, okay? Okay, well, what is integration by parts? U dv is equal to uv minus v du, right? So now, notice that I only need to do integration by parts on that term alone, right? So my wk is equal to wk du dx, all of this evaluated at 0 and L, minus k du dx, well, I'll actually put it dv dx du dx. And notice that now, indeed, this term shows up. And we have to evaluate at L minus the evaluation at N. So actually, that minus is going to be absorbed by that N. And indeed, this whole expression here is our prescribed heat flux. And so to put the final version of this formulation, we're going to have integral 0L W is equal to this term did not change at all, so the heat source is there. That, of course, is heat that is generated inside the bar, right? It would be like the similar to the body force in the one-dimensional case. And then we have this guy. Okay, and in this case, this whole thing here is going to become our bilinear form, and that whole thing here is going to become the linear form. Yeah, and so now the objective is going to be find u again in some nice set or space of functions such that BUW is equal to L of W. Remember, I forgot here for all W in this, for all W in that energy space, right? And that's pretty much the weak formulation. Yeah.
Shouldn't there be a minus sign for the linear term because we have positive f on the left hand side?
So there is an issue here because, of course, we said that this whole sign situation was going to get absorbed by n, right? So this is essentially, I'm going to rewrite this term here as oh. Yeah.
I was mostly talking about the F, the applied heat flux.
This guy?
Yes, because it's in your weak formulation, it's on your left side, and then you move it to your right hand side.
Yeah, but keep in mind that this term is negative, huh? So when you do the integration by parts, this guy stays on this side of the equation, the same as that guy, right? And the other one, this has a negative sign, goes to the other side. Yeah? Question? No problem, no problem.
Why did you add the first part in the linear form?
Third part?
The W0 Q1.
Yeah, so I just rewrote. It's still same as part of the linear form. I just rewrote it just to make it explicit that now we are evaluating the heat flux at both ends. It's the same thing, basically. Yeah? All right, so this is the weak form. And of course, we are still living in an infinite dimensional space. So there is, of course, one thing that we have to say about our energy space. So our E of omega is defined, if you remember, as the set of functions V that are, of course, square integrable, right? But also, the evaluation in gamma U had to be equal to 0, and that allows us to eliminate from the formulation potential reactive heat fluxes that we may have, right? If you remember that we played this trick, we chose the functions in that way. You have a question?
Yes, in the term on the left, isn't it k dw?
Oh, yes, thank you so much. Thank you so much, yes. A mistake there. Okay, of course, now that we are still living in an infinite dimensional space, we follow the same procedure. We choose functions from a finite set, right? And those functions are going to be basically helping us construct our finite dimensional problem. And so now we call that the Galerkin projection. And then that we are living in a finite dimensional space, we can get the solution to this. So now we go to the Galerkin form. Where we obtain the discrete equations by choosing our trial function, now we call it trial function, UH, and our test function, WH, from some VH, where VH is of course a subset of what we define as our energy space. And so the Galerkin form in abstract form is again going to be something similar. So find UH belonging to that VH such that BUH WH is equal to L WH for all WH in that set BH. And remember that because these both are taken from the same set, we call that the Bubnov-Galerkin approach. And so, for instance, if we're using the same bilinear shake functions that we use for the bar, our UH can be written as a function of x, again, as the sum I phi I of x ui. Ui are the coefficients, degrees of freedom, and then the same with this guy. Right? And this eventually leads to our system Ku is equal to F, where K is the result of applying that assembly operator in the so-called local stiffness matrix. Of course, it's not a stiffness matrix. We have now some sort of conduction matrix, characteristic matrix. And then we're going to have our right-hand side F that is also going to be the result of applying our assembly operator into the local vectors. And that is essentially our problem in 1D. So it's very straightforward. Notice that it is really very, very, very simple. I would say it has the same complexity as the 1D for elastostatics, right? We have a scalar field. We do integration by parts, which is straightforward. Boundary conditions arise. So all good. So now that we have this problem in 1D, the objective is to move it to higher dimensions and learn in the process what are the little subtleties that we have. So now we're going to move to heat conduction in 2D and in 3D. Yeah, we're good. Okay, well, as usual, we are going to start with some mechanics potato that again we call omega. There is going to be a part of the boundary where we are going to fix a displacement field that we're going to call gamma u. There is going to be a normal to that boundary, a normal field, normal vector field, right? There is going to be another part, there's going to be another part of the boundary by crosses that we're going to call gamma h. This is where we're going to prescribe the Robin boundary conditions, and of course the rest of the boundary where we're going to have some sort of heat flux or Newman boundary conditions. We're going to call that gamma t or gamma q. I don't know what I call it earlier. Gamma t, just to have it similar to the one-dimensional case. Okay, but before we get there, now we're going to be dealing with vectors and tensors, and so I will put a little bit of a reminder. This is something that you should already know from previous courses. So the gradient of a scalar, right, by definition is a vector, right? So, and it's defined as ds dxi ei. The gradient of a vector is a tensor, and so is defined as vi xj ei tensor ej. And now we are going to look at the divergence. And if you took the divergence of a vector, by definition is a scalar, and it's defined as dvi dxi. And if you take the divergence of a tensor, is a vector, and is by definition is the derivative of tij, so the ijth component of that with respect to xj ei. So just as a reminder, because now that we move to higher dimensions, we're going to have to deal with some identities, okay? Oh, I forgot to mention here that normally, again, as usually we do it in all problems, we're going to define our boundary of that domain, right? Normally, it's also denoted as d omega, and we're going to use the closure minus the open set, and that is the way mathematically people use, they are used to define the boundary. So remember, the closure is everything that is contained in the set plus its boundary. So if I take, which is a kind of a weird way to define the boundary, I take everything that is in that set plus the boundary minus everything that is in that set, that defines the boundary. So it's a strange way that we do the definition of the boundary, but this is the way it's done. Okay, and remember that these portions of the boundary where we're prescribing these different boundary conditions are mutually exclusive, or they are disjoint. That essentially you can write mathematically as gamma u intersection gamma t intersection gamma h is equal to the empty set. That is the way we normally say that you can, at a given point, you cannot prescribe two types of boundary conditions, right? It's just the way we say. Okay. So now that we have this, we're ready to start again. And remember, we're going to follow the same process. We're going to go from strong form, weak form, Galerkin form. That is the way we always find our discretized finite element equations. So now, given K, that is now going to be actually a tensor, domain is omega, and because it's a tensor, it's in RD cross RD, right? We have our heat source. This doesn't change because it's a scalar field, and that is the nice thing about the heat conduction problem. Before we go to the elasticity in 2D and 3D, right? Because, well, the body force is actually a vector. The heat source here and the temperature field both are scalar fields. We have our prescribed temperature, that is also scalar. We have our prescribed heat flux, that is also scalar. And we have some film coefficient that we are going to assume that is going to be a scalar field, right? Just one coefficient that at a given point is going to relate how heat is going to be transferred from that body to the environment. Remember that the Robin boundary condition had this U infinity that we normally say, well, it's a temperature of the environment, okay? All right, so now the strong form is find U, our temperature field, such that the divergence of K, the gradient of the temperature field, and this whole thing is a vector, that's why I write it like this, plus F is equal to 0. I don't know if you notice, but this is the gradient, but the moment I use that operator with a dot, that is the divergence operator, right? That's also normally the way we read it in papers. Or at least is one way. Some people use div. I like to use it to write it like this. Okay. And this is, of course, in the domain. And then we have the usual U is equal to U bar, which is prescribed temperature on the portion of the boundary where we're prescribing the directly boundary condition. Then we have K grad U dotted with N. N, remember, is the normal. This is the definition of our heat flux. Notice that indeed here we have a tensor, and then we have the gradient of the temperature, which is a vector, right? So this whole thing is a vector, right? Because a tensor operating on a vector is still a vector. And then when I dot it with N, which is a vector, that's a dot product, then I get a scalar, all right? So this is on gamma t. And then I am missing the last boundary condition, which is the Robin boundary condition, which, if you remember, looked very similar to the Newman boundary condition, only that now we have H, our heat transfer coefficient, U infinity minus U, and that is on gamma H. Okay, straightforward, and we do the same thing. And I'm going to go, faster than before because essentially it is the same thing, all right? So now we go to the weak form. So who can tell me what we do? What do we do?
Multiply by a test function.
We multiply by a test function and
integrate it through the whole domain.
and we integrate it on the whole domain. My whole domain is now omega, right? I have d omega, and we set that equal to 0 for all test functions in some space bh of omega. Yeah, notice that this is a scalar product, right? F is a heat source, is a scalar field, and then we talk about this whole thing. So we have a tensor here operating on a vector, which is going to be a vector, and then when we take the divergence of that, we get a scalar plus scalar is scalar, multiplied by scalar, we get a scalar, okay? It's all a scalar equation, which is very, very simple. All right, let's do, so let's try to deal with this term here, because again, the objective is going to be to balance the derivatives, right? Now, because of this grad u and the divergence applied to that term, we're going to be dealing with a second derivative on the temperature field. So we want to lower that requirement, not to make it so stringent, right? And so we are going to work on that term. Well, this term plus grad w dotted with k, grad u is equal to the divergence of this whole thing. So this is an identity that is very simple to check. Believe me, and if not, check it in the book. But that is the identity that we're going to deal. So notice that now this term, that is the original term, this guy here, right? Now it's like you apply the derivative to the second term, and then you apply now the derivative to the first time, and that whole thing is the gradient of that whole operation. So if you want to look at it in what are the types of objects we're dealing with, we know already that this whole thing is a scalar field, right? Well, let's see the second term. Here we have a tensor operating on grad u, which is a vector, so that is a vector, and this whole thing here is a vector. So the moment we do the dot product between the two vectors, we get a scalar, and the same thing here. So this guy here is a vector, tensor applied on a vector is a vector, and now we have this scalar field applied on a vector is a still a vector, and then when we take the divergence of the vector, we get a scalar. Well, so that is the identity that we're going to use, and so we get, when we replace this guy, right, which is equal to this whole thing, into the original expression, we're going to get something that looks like this. Is equal to the integral of this, which did not change as in the one-dimensional case. But now we are going to have the most important difference with respect to what we have done before. So we're going to have to deal with this term, which is basically the divergence of w k grad u. And this is a new term. So we're going to work with that term, right? And we're going to use something called the divergence theorem. Because remember, we're trying to get our boundary conditions from there, but we have an integral over the volume, right? So by applying the divergence theorem, and you should all know what the divergence theorem is by now, right? We're going to transform that integral over the volume into an integral over the boundary. And how is that? Well, the divergence theorem basically just states that that integral, that is computing the divergence on that quantity, is equal to an integral over the boundary of that quantity dotted with the normal to the boundary. That is just simply the divergence theorem. Of course, mathematically is known. There are proofs dotted with the normal. And that is how we give rise to the boundary conditions, or Newman boundary condition. Actually, Newman, Robin, and perhaps the boundary condition that is dealing with the reactive fluxes. So when we put that back into our whole expression, we have integral over omega. So this does not change. It's the same guy, this guy. This also does not change. But now we have an integral over omega of this whole quantity, dotted with n. Right? And now if you look back to the definition of our boundary conditions, that is basically these guys here. Remember that this integral is over the entire boundary. So in fact, we have to replace this one integral by the integral over gamma u, gamma t, and gamma h. And so what we're going to do now is just simply replace those integrals by the actual boundary conditions, noting that a priori we're going to remove the reactive heat fluxes the same way we have done it in elasticity, right? And so now that becomes, let me just, plus, actually, is going to be integral gamma h w h u, the gamma, right? And that is the term that is going to be unknown, arising from the Robin boundary condition. I will explain a little bit more about that. On the right hand side of the expression, we're going to have our heat source that does not change. And now we are going to have the Newman boundary condition. So it's W prescribed or Q bar. And we are going to have the other term of the Robin boundary condition, that is the unknown, sorry, the known part of the boundary condition. Because remember, the U infinity was our ambient temperature. So that is the thing that we know. And if you remember, everything that we know is going to sit on the right-hand side of the expression, and it's going to somehow modify our final F vector, right? And so this guy is WH U infinity, and I'm running out of space. D gamma. And so when we are looking at all these components, you see that, well, everything that is here is defining my bilinear form, and everything that is here is defining my linear form, right? And just to recap what I'm doing, and I'm going to go very slowly now on this term here is basically repressed by three integrals. One where this guy is gamma u, another one where this guy is gamma t, and another one where this guy is gamma h, right? We're going to remove the one from gamma u because, again, we are going to make these test functions vanish at that part of the boundary. So those are dropping from the integral, so they are zero, right? And the other two are going to be replaced, one by this guy and the other one by that guy, right? And so that is why you see here, these two terms here are the Robin boundary condition, and this guy here is the Newman boundary condition. And when you look at the Robin boundary condition, well, the Robin boundary condition indeed has two parts. One that you don't know, that's why this part is here on the left, where this is the guy you don't know yet, right? And the part that you know, and you know it because you assume that that U infinity is your ambient temperature. Yeah.
So you can see the right side of the equation basically as the heat driving forces, and then the left side of the equation basically what it does with the temperature combined with the material characteristics.
Yes, pretty much. Yeah.
Like earlier, we don't include the primal field because we want to account for the boundary conditions and find in a way the ends of the boundary.
Yes. Yeah. So now you don't have ends of the bar, but you're prescribing the boundary conditions over your entire boundary, right? Okay. So now, just simply to finalize this, we're going to simply state this in abstract form as phi u in that space such that BUW is equal to LW for all W in that same space. And with this, we are pretty much done with the heat conduction problem. This was a long lecture, so it's basically 45 minutes. So we stop here. But everything that we did here is going to help us go into 3D elastostatics. Any last questions? So let's take a break because this was actually a long lecture, okay?